dt, p dot, and p prime of t all mean the same thing. True. Yeah, they're all different notations for the derivative of p with respect to t. True or false, parameters are quantities that do not change over time. True. Right. That's in contrast to the dependent and independent variables, right? Those things change over time. All right, 3 approaches for analyzing the solution to a differential equation. Yep. Yep. Analytical.
How do you make that? I didn't get the last one.
Then you got it wrong. Yeah. Yeah. This one's wrong. If you said numerical instead of quantitative, that's okay. No. Okay, so we saw last class that the Malthusian model, which had the underlying assumption that populations grow at a rate proportional to the size of the population. It matched the data well. This was the US population data. It matched really well up until about 1860. And then the model starts to take off really fast, but the actual population growth didn't keep up. Okay, so it starts overestimating. So we're going to adjust our assumptions about how populations grow, try to make a better model. Okay, so our next model is called the logistic model. So we're going to start with the Malthusian assumption, but we're going to say that only holds while the population is small. When the population is small, the rate of growth is proportional to its size. But then we're going to add an additional assumption that if the population gets too large to be supported by its environment, then the population size will decrease. That is, the rate of growth becomes negative. So this indicates that there's some kind of carrying capacity, right? Because there is some value that is too large. So our variables and parameters, we've still got P and T, right? So P will be population. We'll still have T be time. And now we had a K in the Malthusian model, which was the constant of proportionality for the assumption 1. Okay, and then in assumption 2, we've introduced this concept of too large, right? So we're going to introduce a new parameter. Doesn't change over time. This is a constant thing. A new parameter that represents what too large is, like the carrying capacity, the critical size of the population. Typically, that's called N. Okay, so I've created all the variables and constants that I need here, parameters. I'm going to try to build a model that matches these assumptions. The constant of proportionality, right, when they say proportional in that assumption 1, there's always a constant of proportionality. Okay, so this is what mathematicians do. They say, okay, this is what really happens in real life. I'm going to try to create a mathematical equation. I'm going to mess around with these variables and parameters to create something that behaves that way, to create something mathematical that behaves this way. All right, so both of these talk about the growth rate, right? The rate of growth and the population's rate of growth decreases, right? Either it increases in proportion to its size, or maybe it decreases if it's too large. So how do I represent the rate of growth of the population? dp dt, yeah. The derivative, yeah, is the rate of growth. dp dt. Okay, and then if we look at assumption 1, it's just the rate of growth is proportional to the size of the population. That's the Malthusian model that we came up with last class, KP. But then we have to adjust this model a little bit to make the rate of growth become negative. if the population is too big. So k times p, assuming k is a positive number, k times p is going to be positive, right? All right, so I'm going to multiply by something. So I'm just going to put something in parentheses here. I want it to be close to 1 if p is small. Okay, because if p is small, we're just going to use the Malthusian model, right? When p is small, it's just the population's growth rate is proportional to the population size. So I'd like this thing in parentheses here. I want it to be close to 1 if p is small. I want it to be close to 0 if p is close to n, right? If we're getting close to the carrying capacity, that means that the population is not going to be changing very much. It's not growing very much because there aren't enough resources. And then if p is bigger than the carrying capacity, I want it to be negative, because then I'll have a negative quantity times a positive, and my whole rate of growth will be negative. So let's write down all those things that I want. Right? I want this factor that I'm going to add here. I want it to be approximately 1 if p is small. I want it to be, what do I want it to be? Close to 0. Yeah, I want it to be close to 0 if p is close to n. Right? If we're close to the carrying capacity, the rate of growth should be slowing down, should be approaching 0, holding constant. All right, and then I want it to be negative if p is bigger than n. If we've surpassed the carrying capacity, I want that factor to be negative because it will make my whole rate of growth negative. All right, so here's what a really smart mathematician came up with. He said, let's look at the factor, the expression 1 minus p over n. If p is really small, like close to 0, p over n is a really small number. So you have 1 minus something really small, which will be close to 1. Okay. If p is close to n, what is p over n close to? 1. Then 1 minus 1 would be 0. Right? So then my rate of growth would be holding constant. The rate of change would be 0. All right, and then if p is greater than n, then this fraction would be bigger than 1. I get a negative number here, and my rate of growth will now be negative, right, to bring the population size back under the carrying capacity. Does that make sense? Okay. So that's sort of how you build a model. You have to you just play around with your parameters and your variables to try to make it do mathematically what it actually does in real life. All right, so rather than giving you the solution to the logistic model, right, there's some function p of t or a family of functions p of t that will solve that equation. But rather than giving it to you, we're just going to think about what the solution functions will look like qualitatively. So we're going to start by looking for equilibrium solutions, constant functions that satisfy the differential equation. Any function that's a constant, what is its derivative? 0, right? So if the population was always 8, whatever, rabbits or whatever, then its derivative would be 0. Constant function is not changing, so its derivative is 0. So to find equilibrium solutions, we set the differential equation equal to 0. So I'm going to set kp times 1 minus p over n equal to 0. And I have two factors multiplied together. The answer is 0. Whenever you have two things multiplied and the answer is 0, it has to be that either one of them is 0 and or the other one is 0. So in this case, p of t, my solution function, is 0. And over here, if I solve for p, I get p equals n. P of t equals n. So do those two functions make sense as equilibrium solutions? Yeah, if there were never any members of the population size is always 0, it will never grow, right? There are no members to reproduce. And if the population size is at its carrying capacity, it doesn't grow or shrink based on our assumptions, right? It will just stay at the carrying capacity forever. So those are our equilibrium solutions. So I'm going to try to use those to create a visual of what any population will do. So I've got time and population. And I want to try to sketch what's happening. So I know that at n and at 0, I have equilibrium solutions. So I'll put those in. Oh, that's not very contrasty. Yeah. Okay, so this one is P of t equals 0. Okay. And then I have another equilibrium solution at n. And then based on our assumptions about populations, we can think about what happens for any initial condition, right? What if our population starts out somewhere bigger than 0 but smaller than n? What's it going to do? It's going to grow to n. And based on our assumptions, it's going to start out growing Malthusian-like, right, in proportion to its size, which means exponential, kind of fast. But then it slows down as it reaches its carrying capacity. So it might look something like this. But if I start already really close to the carrying capacity, right, it might never have that sort of slow down, that really fast growth. It just approaches slowly. And what if I start above the carrying capacity? It'll come down to the carrying capacity based on the fact that this factor would be negative, making the whole rate of change negative. So my function would have to be decreasing. So I've sketched the solutions, several solutions to my differential equation without solving anything. This is what we call a qualitative analysis. I kind of know a lot about what these do without having any technique for how to solve it. But don't worry, next class I will teach you an analytic technique so that you can just solve it for P of t. Okay, but we're going to practice a little bit more with modeling before we get into techniques of solving. We're going to adjust our assumptions one more time about how populations grow. This time we're going to add in another important variable, the fact that species don't exist in a vacuum, right? It's not just about resources, right, but predator and prey dynamics. So we're going to try to model a predator-prey system. We're going to call the prey rabbits and the predators foxes. And since each population influences the other, right, foxes need rabbits to be able to survive because they eat them. And rabbits don't do well in the presence of foxes, right? So they influence each other. We're going to model both populations at the same time. So here are our assumptions. They may be overly simplistic, but this is how we start. You start with a simple model and you complicate it a little bit at a time. All right, so if no foxes are present, the rabbits are going to reproduce at a rate proportional to their population. So we're not going to impose a carrying capacity on them. We're just going to say that it's a Malthusian model if there's no foxes. Foxes eat rabbits, and the rate at which the rabbits are eaten is proportional to the rate at which foxes and rabbits interact. The more often they run into each other, the worse it is for the rabbits, right? And then without rabbits to eat, the fox population will decline at a rate proportional to itself. And the rate at which foxes are born is proportional to the number of rabbits eaten, which by the second assumption was proportional to the rate at which the two interact. So I have 4 important assumptions, and I'm going to use them to write 2 equations, one for rabbits, one for foxes. So let's first identify our variables and our parameters. So we'll have R be rabbits, F be foxes, T will be time. So those are all our variables. Those are the only things changing in time, right? Number of rabbits, number of foxes. How many constants of proportionality am I going to need in here? How many parameters? 4. Yeah, there's 4 assumptions, and they all say something about being proportional to, right? So proportional, 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 proportional. So I'm going to need 4 parameters to describe those constants of proportionality. So let's call them alpha, beta, gamma, and delta. Alpha, beta, gamma, and delta. These are my parameters. Constants of proportionality. Sorry, gamma's like that. Yeah. Okay, so those are all the things I'm going to need to build the model out of. I'm going to write 2 differential equations, one for rabbits, one for foxes. So I have dr dt, the rate at which the rabbit population changes, and df dt. All right, so let's think about the rabbits first. These 2 first assumptions have to do with rabbits, and the second 2 have to do with foxes. Okay. All right, so for rabbits, if no foxes are present, the rabbits reproduce at a rate proportional to their population. That's just the Malthusian model. So we'll use our first parameter alpha instead of k that we used before. So alpha r. So this is what happens if there are no foxes. dr dt just is the rate just changes in proportion to the number of rabbits there are. More rabbits, the faster the population grows. All right, and then the second assumption says that foxes eat rabbits, and the rate at which the rabbits are eaten is proportional to the rate at which the foxes and rabbits interact. All right, so when foxes and rabbits interact, do you think that makes the dr dt bigger or smaller? Smaller. So let's subtract. Take away from the rate when foxes are around. And it's important we take away from the rate in a way that's proportional to how they interact. So I'll use my next constant of proportionality, beta. And then there are lots of ways that I could mathematically model foxes and rabbits interacting. One handy way is to just use R times F, rabbits and foxes. Right? So if there are more rabbits or more foxes, when you take the product of the 2, that number gets bigger, right? All right, let's look at the fox assumptions. Without rabbits to eat, the fox population declines at a rate proportional to itself. This is almost Malthusian, except it means the foxes are going to go extinct instead of growing forever, right? So my constant of proportionality could be gamma times foxes, but I'm going to make it negative, meaning the rate of growth is negative so that the fox population is declining. So there's no rabbits there. Yep. No rabbits yet. Without the rabbits, the fox population declines. All right. And then the last assumption says that the rate at which foxes are born, so this is the rate at which the fox population grows. So we're going to add here another term that increases the rate of growth of the fox population in a way that's proportional to the rate at which foxes and rabbits interact. Delta RF. it might not be the same. Yeah. So RF is the same. The constant of proportionality might not be. It might not affect the two populations in exactly the same way. Yeah. Right. The number eaten would be the same, but it might affect the size of the two populations differently. Yeah. All right. So this is called a first order system. Okay. It's a pair of equations together. Okay. It's called a first order system because there are only first derivatives present. It's a system because there are two equations, one for rabbits, one for foxes. And since the two functions depend on each other, you can't just solve one and then the other, right? You have to solve them simultaneously. And it turns out that there's simply no analytic way to do that for most values of the parameters alpha, beta, gamma, and delta. So you have to either use a qualitative or a numerical method to study the solutions. We're going to start by doing a really simplistic version of a numerical method. Okay, so one way to study a solution numerically is to pick initial values for R and F, or study them in the field, get some initial values for R and F. Okay. And then you can use those values of R and F to calculate values of dr dt and df dt, so you know how fast the populations are changing at that initial value. And then you can use those rates of change to estimate the values for R and F some small unit of time later. So we'll try it. If R of 0 is 12 and F of 0 is 2, we're going to pretend all the parameters in the model are 1 just to make it look nicer for now. So my equations are dr dt is R minus RF, and df dt is negative F plus RF. And we're going to assume that R of 0 is 12. And F of 0 is 2. So I now know a value of R and a value of F. I could plug those into my two equations for R and for F and get values for dr dt and df dt. So that's what I'm going to do. I need more space, sorry. Okay, so dr dt is now going to be R minus RF. I'm going to replace my R's with 12s, which is negative 12. And then df dt is negative F plus RF, so it's going to be negative 2 plus 12 times 2, which is 22. All right, so let's interpret what these numbers mean. If we give them some units, it'll be a little clearer. What are the units on dr dt? Yeah, or per whatever time unit. I haven't specified yet, but this is rabbits per time unit. And df dt would be foxes per unit of time. Okay. So I now know how the populations are changing. I know that when at time 0, dr dt is negative 12, which means that it's changing by negative 12 rabbits per day, whatever. Okay. So 1 day later, right? You know, like in movies when they do this, 1 day later, right? So I can think about what happens, what's R of 1 and what's F of 1. So R of 0 was 12, right? I started with 12 rabbits. I changed by 12 rabbits per day, decreased by 12 rabbits per day, so I take away 12. The rabbits have gone extinct. There are no more rabbits. Okay. And then my foxes, I started with 2 foxes. They grow by 22 foxes per day. So I add 22 to that population and I get 24 foxes. Put some units here. Rabbits, foxes. So I now know the value, or an approximate value at least, of R of 1 and F of 1. How many rabbits and foxes there are 1 day later. And I could repeat this process over and over and over again. I could say, now take your 0 and your 24 and use those for your new R and your new F in the differential equations. Get a new dr dt and a new df dt. See what happens. Yeah, rabbits are done. Yeah, once you hit 0, they can't. And then the foxes are going to be done pretty soon because they have no rabbits to eat. Yeah. Yeah, you're typically given initial conditions, but you also would want to, sometimes we investigate lots of different initial conditions and figure out, are there initial conditions that would lead to an equilibrium, or are there initial conditions that make both species go extinct? And that's part of what we do in our analysis. Right? And you have something very similar to this in your project at the end of the semester. What's up?
I was just wondering, because the rate for the rabbits is now 0.
Yep.
Then foxes would make it 4.
Right, which means that at the next step, foxes are extinct. Yeah, good. Yeah.
So for this, why did we change the model for F? Oh, that's because that's not DFT, that's just
Right, right. That's just the function f. We took how many there were to start with, and we looked at df dt, the rate at which they're changing. Oh yeah, absolutely, yes. Yep. Yeah, you can always complicate these a little bit more. We could add a carrying capacity to both populations. All right, so that finishes up the lecture part of class. I'm going to have you start working on the activities. Oh, I have one last thing to say, sorry. So we've seen 3 models now, the Malthusian model, the logistic model, and a predator-prey model. And 3 techniques for studying their solutions. Analytic. So far, all we can do is check that a function is a solution. I'll give you a differential equation. I'll give you the solution and say, verify that it's a solution. But we'll be able to actually find solutions next class. But then we can also do qualitative analysis and numerical analysis. So what we just did with the predator-prey was a numerical analysis. The next 3 sections of the text are going to further illuminate those 3 techniques. But for now, we're just going to focus a bit more on modeling for today's activities.